Next, I am please join me in welcoming Jason from Datadog.
Hello, everyone. My name is Jason Moiron. I'm a staff engineer at Datadog, and I'm here to talk a little bit about our observability data pipelines. So for those of you who don't know, Datadog is a monitoring and analytics company. It's kind of an exciting time for us because we're IPOing tomorrow, like a couple blocks away from here. Woo! All right. Thank you. So this has put us in a bit of a retrospective mood, and I can't resist kind of going meta. So observability kind of focused conference, observability data pipelines instead of actual observability. So the agenda for this talk, it's kind of split into three main themes. They kind of intertwine. It's not exactly like one section after the other. The first explores the data that we get and the constraints that the monitoring use case applies to that data. The second explores kind of architectural patterns that we have adopted to deal with that data. And finally, how we actually observe that and how we kind of make sense of it. Great. So this is kind of like the center square in observability bingo. So you're welcome if you're playing along. I briefly wanted to talk about this, though. If you're in like dissys Twitter, or if you spell observability with an 11, you've probably kind of seen this before. It's like an educational tool. Like we're trying to get people to understand more about observability. Monitoring is like a very kind of tactile sort of thing. Like a monitor is a noun. You can build monitoring. You can buy monitoring. So when you see this, you're like, well, I have monitoring, but you're kind of like FOMO. Like, what's observability? And I kind of prefer this formulation. Like observability doesn't necessarily like. It isn't not monitoring, but it isn't monitoring either. And observability is a lot more of like an abstract concept. So like, how well do you understand your systems by the outputs that they have? That's basically how observable they are. You can add new data and new telemetry to your systems, but if they don't increase your understanding, then the observability hasn't really gone up. And you can also add new tools to examine old data. But if you're not changing the systems, then it's kind of a gray area on like whether or not you've actually increased the observability of those systems. Despite all of that, observability is about getting like, useful signals out of data from our systems. And if you're getting these useful signals, you shouldn't be like watching them yourself. You should have computers watch them, and that's what monitoring is. So if you have like new signals, you should monitor them. Not doing so is like writing unit tests and then not running them and not having CI. So for the purposes of this talk, I'm going to focus a lot on the monitoring use case because that's actually a significant source of challenge that we have in our data systems. So this is a monitor. We use the groundbreaking color scheme of green for good and red for bad as well at Datadog. You might have heard about this earlier. This is just a query executed on a 1-hour window repetitively. And this is a monitor that is looking at latency for one of our actual data systems. So you can see there's this periodicity. Every half hour, latency kind of gets bad, and then it's fine again. There's a lot of different reasons for this in our architecture, but it's a really common pattern because there's a lot of scheduling involved in serving up monitoring data. So these monitors are being executed on a schedule, and we can add some jitter to that, but it's still a little bit difficult sometimes. And there's also schedules that we can't jitter around because they're user-initiated, like batch submission or user cron jobs. Dashboards reloading, et cetera. All these things are kind of like these repetitive scheduled reloading processes, and they cause this kind of like really obvious latency tick in a lot of our data. And so a lot of our engineering effort is focused around like getting rid of these so that we can capacity plan a little bit better. This is a dashboard. Hopefully, a lot of you hate these. You shouldn't be looking at these, hopefully. However, they are really great living documents for a system. So if you have new engineers and you want to onboard them in the system and you want them to have some kind of like tangible connection between the system that they're writing and the actual like behavior in production, then this is actually a pretty good way of kind of describing that in a visual way. So the bottom right, there's like a kind of a faint gray line across the top, and that's like an outlier where a system is hitting this cache 150,000 times a second. However, the sort of like red-orange band is showing that these are not actually going through to disk. And this is another really common theme in our systems. So this is actually the same system that we had the monitor for, and it shows that this cache is really doing a lot of heavy lifting. And we have these really heavily read outlier batches of data, but caching really works really well for this kind of repetitive use case. And finally, to satisfy the rule of 3, some logging data. This is like much less visual than the previous 2 slides and seems quite different on the surface in a lot of ways, but the use cases are actually really similar. Like the way that it kind of impacts the data stores and the structure of those data stores is similar. So all 3 of these visualizations contain right now. They all also contain history, which is really important for establishing patterns. They all have a really, really small portion of a really large data set. And they all have like a repetitive read component to them, like what's new, what's new, what's new. And part of that is because they contain now. So this is kind of like a satirical sort of onion headline version of like how to approach observability. And this is actually mostly what we do internally, and it's mostly what our users do as well. And it actually ends up being like a pretty successful first approximation for how to approach it. As long as you can kind of like build institutional knowledge on top of the data, then having the most data you can possibly collect and having the most data you can kind of afford to collect is a good thing. But because this is popular and because it works, it means that we get a lot of data. So we do collect all sorts of different types of data at Datadog. We have traces and logs and network stuff and container, like tons of different things. But I wanted to use metrics as a sort of example. All of the different types of data have their own peculiarities, but they have a lot more similarities than differences. And I think metrics is an older sort of an older data type that more people kind of understand intuitively. So this is kind of some sort of facts about metrics data. Despite the challenges in meeting the monitoring constraints for metrics data, there's actually a lot to work with. Almost all reads are from right now, or include right now. Almost all writes are also to right now. Like metrics are essentially append only, same as logs. We can chunk really aggressively in time. We can shard aggressively in time because your memory use from an hour ago is not going to change because your memory use right now has changed. We can also chunk and shard really effectively in space as well, because your memory use and your CPU use are not necessarily related. At least the recording of those are not related. However, when people go to kind of navigate their data, all of the sort of repetition from all of the automated systems that are querying this data, like anomaly detection, dashboards, monitors, they don't hit those queries, so we don't actually know that they're going to happen. If you're creating a new dashboard, creating a new monitor, or you want to kind of see something in your system, you don't hit hot data, you hit cold data. And this is actually the entire user experience of the site. So a lot of our engineering time is actually focused on making cold data reads really good instead of hot data reads. So an example of a cold data read, this is a 1-year view on the number of hosts in a particular cluster. It gets kind of funky. Those are actually not kind of artifacts from bugs, but like real cluster rotations. And this is basically each host is submitting a kind of heartbeat with the value of 1, and then we kind of sum those all together. But if we needed to do this on like the raw data and we submitted data every 10 seconds, this would be like 500 million points for this one line. And we would need, like without actually aggregating it in time as well, we would need a 3 million pixel wide monitor. So like that's no good. So of course we aggregate this ahead of time in time. So we'll like average and then sum everything and keep much lower resolution data around for this kind of use case. However, this is write amplification on like a vast scale, and we can't mix this with live traffic. And that's kind of like a theme, like, oh, we can't mix this use case with live traffic. We need to have something else. Oh, we can't mix this either. And this kind of plays out in the way that we've structured everything. This is another use case. Instead of having like one line or one like kind of output created from many, this is like grouping by many different outputs. So each one of the hexes here is a host, and then we've done a query for some metric like CPU utilization or something to kind of color all of those. We call these kind of wide because they return like a large number of results. And this can actually get much, much wider than this. This is just a nice visualization for like how wide they can get in sort of a normal case. But say you had some kind of throughput metric on some endpoints, and you wanted to know what the sum of your throughput was, and you had 5 million endpoints. And you could sum them all together to get one, like the previous slide. But you could also want to see the top 10, and then you would need to produce all of them and throw out most of the data. So there's other use cases that are kind of challenging. There are other use cases that people kind of encounter as well. A lot of these use cases, caching is really effective, but some of them are not. Dashboards are interesting because they're parameterized, so you can go from reading the same data over and over, like really hot data, to reading completely cold data just by changing a value. But the takeaway from this is that a lot of these use cases require like specialized applications, like in some cases, specialized data stores. And so we needed infrastructure to actually kind of deal with that. Excuse me. So here's kind of like the cartoon version of the initial infrastructure. Basically, grab all the data from the user and then toss it in a log. If you're designing a data system, this should be like your first thought because logs scale really well. Unfortunately, usually you don't want to just read out data as it came in and like present that to the user because it's nonsensical. We're push instead of pull because it's better. It's easier to absorb kind of large scale-ups, and we don't want our like users to have our system kind of reaching into their system and pulling out data. This type of a system makes it easy to add new features. It's very flexible. And so we had things that we wanted to do, like throw away bad data or apply metadata based on the source of the reporter from the user system, or identify and create entities in the backend, et cetera. So we kind of just duplicated it. Now, there's reasons not to duplicate it. Queuing theory tells us that if we add queues, we add latency, and we don't want latency because it's bad. Queues are also difficult to plan capacity around, and they add kind of complexity. Like this has twice as many systems as the previous slide, and they add latency, obviously. But what we get for that latency is increased throughput, and we also get resiliency because a lot of these things are backed up, and flexibility, and kind of common interface for our data. In order to understand what's going on here, let's look at some of the things that we measure about this. So some of the kind of key metrics that you want to measure if you have queues. Latency is kind of obvious because that's the thing that you're making worse by adding the queue. There's also lag. Lag makes the networking people a little more relaxed because they want to own the word latency. Lag is equivalent to latency when you're measuring it in time. You can also measure it in number of messages or number of bytes, and then it becomes a little bit of a different signal. Throughput, which is the number of messages going through your queue, and load, which is something that I'll explain in more detail in a minute. So here's a really sort of simple first approach at measuring latency, which is just adding timestamps everywhere. You can put these in your queue messages, and then you can do interesting things like take only part of your pipelines and add their latencies together. Of course, you should be tracing all of the, well, not all of them, but you should have traces on some of your messages going through the system, so you can also have kind of understanding of where time is being spent. But metrics and distributions are a good way of having a kind of a globalized view of, what part of the pipeline do I need to scale up, or when am I going to need to scale this queue up. It's also really good for This kind of setup is also really good for fan out because all of the different consumers that might be reading the same data, they're going to have their own latencies and their own throughputs and all that stuff. So let's look a little bit about let's see what this looks like, kind of. So here's a system that's in a bit of a crisis. It's falling behind for a while, and then it's kind of catching up. So this is latency of messages, and it's measured in minutes. So it's having a pretty bad time. This on its own doesn't really tell us why anything happened, though. And observability is about like understanding things. So we know that latency was bad, but we don't really know why. So we can look at throughput at the same period, and we'll see that like some of them have like great throughput, and then it suddenly collapses, and it's really bad. We know that all of these systems that are being graphed here, they are all the same. They're working all on the same data. So now we know that, OK, our latency got really bad because our throughput dropped, and we weren't able to handle the data going through the queue. It could have been something else. We could have just had more data, and then we were like not having enough capacity to keep up with it. But in this case, it's like throughput dropped. So why would it drop? And this is the load metric that I was talking about before. So most consumers of queues are set up as a kind of main loop that pull messages off the queue, and then they kind of push out messages asynchronously to some kind of group of workers. And hopefully you do that with some back pressure. Otherwise, you'll just have infinite unbound workers locally, and it'll explode, and you'll get a page. So in this kind of structure, that loop is waiting for messages some percentage of the time. And this load metric is essentially a measure of like how long we spend waiting in that loop versus not waiting. So we can see here that the systems that were kind of falling behind, their load metric suddenly dropped. This is like an inverse metric. So low is very heavily loaded, and high is not loaded at all. But it didn't like completely bottom out. And usually when we have CPU-bound problems, the load just bottoms out because it's constantly being pushed. We're constantly in the part of the loop where we're processing things. So it turns out that these were all new machines, and they were doing really I/O-intensive replication on startup, and so that's why they behaved like this. And this is something, of course, that we knew, and there's like I/O metrics to corroborate this. But these are really important. Like just from looking at the state of the queue and the state of the consumers, like we can kind of understand with only metrics, not even traces and a bunch of other complicated things, what's going on. And this kind of helped us. So this is a story from about 5 years ago. I mentioned retrospective. And at that time, we would get data from our customers. We would write it into this queue. We'd have another thing pull it out, and then we'd write it directly to the real-time data store and to an indexer. Separating data and metadata for metrics is really, really good because they scale their reads very, very differently. And you want to be able to kind of control how that works and scale them up independently. So this was fine. And we liked this because we didn't have to go through another queue. So we thought, oh, this is going to be like the lowest latency, like get the data to the customer as fast as possible. Unfortunately, it had a couple like really big drawbacks. So one of the problems is that we have like now a combined failure domain for the indexing, for the metadata, and for the actual like time series data. Another problem was like once we have a failure, it starts to impact everything, and recovering from it is really painful. So we were willing to kind of pay the latency of adding another queue in that sort of pipeline and move those two sort of boxes off to where the preaggregation thing is. So we did that. And then the overall latency of the system went down. And we were very confused because it shouldn't go down. We added a queue in between the resolver and the indexer and the real-time data system. But we had all of these kind of queue metrics already, and we had like a good established pattern of using them and understanding them. And we realized that when we were doing the writes in the metadata resolver, they were not parallelized. So they were both waiting on each other all the time. And when we put them on the other end of the queue, then there's like this implicit parallelization because now they're like separate consumers reading at different rates. This would have been obvious with tracing, but again, this was in 2014, and we didn't have that. But having the Q metrics made this really easy to see really quickly. Like, we pushed this out, we saw latency drop immediately, and like 10 minutes later, we were like, oh, it's parallelized now. That's great. And this kind of extends down into the applications themselves. So previously, I talked about preaggregation in time, but we also have preaggregation kind of in space, like across dimensions for metrics. So again, if you have like 5 million endpoints and you want to see a sum of the throughput, we can kind of do that in a streaming way and then make the repetitive read of that much cheaper. And we do that with like an internal pipeline of, in this case, it's like channels and worker threads. And we can use the same, we can like reuse the same observability concepts as we did at our infrastructure level. And this is actually really powerful because understanding this type of data and like drawing actual conclusions from them and making improvements to your architecture, there's like a pretty high cognitive overhead to doing that. Even if you design like a really great tool, and it's never going to say, oh, this is the problem. Like, you're always going to have to interpret it, and you're always going to have to kind of build up a mental model. And being able to reuse the same patterns, it allows you to have a very deep understanding of new applications and new pieces of your architecture without having to relearn all the cognitive overhead of like, oh, okay, this is like a new set of metrics, a new set of SLOs, and just a new way to kind of interpret all this stuff. And this sort of repetitive kind of fractal design of like reusing the same patterns is incredibly common all over our infrastructure. And at first it was kind of incidental, and it's become more purposeful over time. So here's another pattern. If there's anyone in the audience who's worked on like RDBMS systems, this looks like essentially like a database. Like, I could draw this diagram and say, this is Postgres, and it would be sort of right if you kind of squint. So it has like transaction log, it has a commit log, it has indexing, it has materialized views, it has tables. It's a database. But it's a database like it expanded out into an architecture. And finally, the last kind of pattern that I wanted to talk about that fits this is leveled compaction. Leveled compaction is like a way of combining data in order to reduce the cost of reads over time and to kind of make your writes look more like a log, because logs are great. We used leveled compaction kind of at the infrastructure level with this preaggregation framework that's like creating these lower resolution data files for us over time. But we also use it in our real-time data store. So all of the really hot data that's involved in metrics that we want to keep really hot, we keep all of that in memory, and then it kind of gets pushed out into this 1 hour chunk, and then we kind of combine those over time into 4 hour chunks because, again, usually people don't want to see like this 5-minute period from 4 hours ago. They want to see the last 4 hours or the last 8 hours or the last 24 hours. So this fits our read pattern really well. It also actually fits our product really well. Like, almost all the timings in all these preaggregation systems are dependent on like the values in this dropdown for how you. So in closing, distributed systems, since it's a discipline and it's like kind of confusing, I think it's clouded our recognition that these patterns repeat everywhere, because when you distribute the patterns, you get these new failure scenarios, and they're kind of complicated. But really, they'll work. Like, the things that you see in an architecture diagram on a wide scale, they'll work when you write your program like that. And when something works in your program, or something is part of like the way that a CPU is designed, that'll work if you blow it up and do that in your architecture. And not only will it work, but you'll get to be able to reuse a lot of the literature around how to observe those things. And you'll, again, you'll be able to lower the kind of cognitive burden and the sort of institutional cost of like teaching everyone else in your organization how to understand these things. So, thank you.
Thank you, Jason. Questions for Jason? Okay, back here on my right, second or third row from the back. Question? Yep, please.
So Datadog is a is a multi-tenancy solution, right? And how you deal with the noise neighbor among the customers?
How do we deal with noisy neighbors? Yeah, so many different ways. Part of that, because everything can be so heavily sharded, we can like distribute data like very aggressively, and so the noise caused by a noisy neighbor is then kind of amortized over a larger set of machines. For not all our customer kind of like size chart is not a bell curve. It's like really skewed. So we have like some customers that are really, really big, and we can basically make them not multi-tenant. We can give them their own stuff, and then they won't bother everyone else. So there's a couple different ways that we do it.
Great, thanks. Another question for Jason. Back in the middle back.
Hi. Just a quick question regarding expanding on the topic of observability. We do use Datadog a lot. Do you have any plans of coming up with some kind of inter-system metrics or some kind of quantifiers to show what is going on? Because what happens generally in a production issue is you have a large-scale picture of just your microservice, and you end up jumping around dashboards a lot in Datadog. Is there like an end-to-end picture being developed to see that, to kind of trace out what happened to this message from where it began all the way down across the jumps in microservices? Is that something Datadog is planning on?
Yeah, we have a APM solution. So we have a distributed tracing, and we're involved in open tracing. So I don't know. I hope that answers your question. We have that. I just didn't focus on that in my talk.
Makes sense. One more question for Jason, please. Here's one in the middle front, third, fourth row back.
How large is your Kafka cluster?
I can't say, but it's really, really big. And we have a lot of them.
That is the answer I expected. We do have time for that. Was quick, so we do have time for one more if anybody else has a question for Jason. Okay, thank you, Jason.
Thank you.